Hello, welcome to all to the fourth Sunday of my making maps session. Today's or this weekend is a long weekend in India, so I was not expecting how many will join. However, whoever may join, I'll continue. Whoever wants to join later or is free to join, and you can see the YouTube video later. So let me directly start with the share screen. Okay. So in the previous Sunday, the last thing that we learned was projections. And before the projections, I introduced you to datum. If you recollect, datum is what defines what is your precise latitude, longitude of any given location on the Earth. If the datum changes, that can change, which I had explained. I had also given a demonstration about how the Greenwich Mean Line itself has changed. Now, there was some more information which I wanted to share, which was not possible that day. So here's some more information about datums. Mostly what has happened is this datum science or datum information keeps improving, and we change it over a period of time. But we should understand that the basis is what? The basis is the geoid, the measured radius or measured radius of the surface of ocean at different different places on Earth, or based on gravimetric measurements. Gravimetric, I don't know whether it's wrong. Gravitational measurements at different places, even on land mass, what could have been the surface of the radius of the surface of the ocean. That is the geoid measurement. So that is the only reality. Geoid measurement or measured geoid is the only reality of the Earth's shape. The ellipsoid or the spheroid, whatever we call, is not exactly a reality. It is a calculated measurement. It is a calculation done in such a way that we can work more easily. So it's a predefined ellipsoid which best fits the Earth's surface. Now, what happens is this spheroid is calculated for our calculation convenience and ease of operation in GIS systems and everything. Now, as I said, as we have better and better measurements of the Earth's surface, the geoid shape keeps changing. Even it changes even with time, meaning not just because of better measurement of the place, but it keeps changing because of the internal structure of the Earth. It keeps changing. Now, which means that the latest geoid or latest measurement what we have would be the best. Yes, that is true. And as I said, WGS 84 is not the latest, but the most accepted standard currently. But is that the only standard? No. What happens is this ellipsoid or this definition of the WGS 84 ellipsoid based on the geoid is so that it is convenient for the whole world. Now, sometimes some countries want to make more accurate maps and they're not bothered about the whole world. Not bothered in the sense that it is not necessary for them to sacrifice the accuracy within their country in order to match the WGS 84 ellipsoid or WGS 84 spheroid for the whole world, because they want more precise maps only for their country. So even though WGS 84 is the latest, we have parallel datums which are in use in different countries, which are basically meant for their own internal, meaning limited area use. So I was aware about it, but I couldn't get a specific example of to demonstrate it with measurement. So that I found last week. So what we have is, if we see the geoid shape, these are the elevations of higher than the shape being higher than the ellipsoid. This is WGS 84 ellipsoid, and the areas which are higher than the ellipsoid are shown in red, and whatever are lower are in blue, and in between are here. So if we see, if I have marked this area, the circle wherever I marked is the Australia, which is generally higher than the reference ellipsoid of WJS84. Now, if it is generally higher, then they are going to compromise. If the Australian people or Australian country uses the WJS84 for which is meant for the whole world for their own country, they are going to have compromises and errors. So they want to make more accurate maps of their own country. So they decided to have their own standard spheroid based on their elevations, local elevations, meaning within that country or in that region. So this is what is called as an Australian national spheroid. I found it the precise thing only last week. So Australian national spheroid is a spheroid that is defined with slightly different parameters. Now here we have this as the Australian national spheroid, that black dimensions, black measurement that we have that I'm showing here is for the Australian national spheroid, and these are the measurements, as we have seen last day, are for the WJS84 for the whole of the world. So instead of this as a semi major axis and minor axis, the definition of the spheroid, they are taking this in black, and which means how much is the difference? So they are taking an additional 23 meters plus on the major axis and 22 meters plus. So they are taking ellipsoid which is slightly larger, and they are fitting it and bringing it in alignment with the surface in Australia, and that is being used as the datum in Australia. Now, with this, what may happen, or what is most likely to happen, which I am not checked 100%, the center of the spheroid will not be at the center of the Earth. It will shift slightly by that many meters or half of that meters, whatever. So that is something which you should know, that datums can be different. For India, for example, we could have a different datum. We earlier obviously had a different datum. There was Kalyanpur and all sorts of Everest datum. There was a datum named as Everest datum for maps in India. And there were others. Now, currently, I'm not sure whether we are using WJS84, meaning the standard maps use WJS84, but is there any specific datum other than the WJS84 datum for India? I'm not sure. So this was the special thing about the datum I wanted to explain to you. Now, now from here, we go to discussion of projection, meaning how to flatten a completely global map, how to flatten it, make it flat, and we can get a flat map. So how do we do that? As we have, as I have already explained last time, I showed you Mosambik, which I peeled and distorted and all that. So it is not possible to flatten a map of Earth, which is a globe, without distorting. That is clear. We cannot flatten it. Distortion will always be there. So how do we do? As I told you, there are different possibilities of what is called as projections. And I explained to you that what is a projection. I'll explain. I just initiated the discussion. A projection, now I will switch off the stop share so that you can see me in a larger dish, and then I'll switch back to the share. So what I do is I want a flat map. So I take this paper or a flat surface or a flat plane and take the globe of Earth here. Or for simplicity or for clarity, I can use that bigger ball, which is slightly bigger, so a little easier to explain. So I keep this paper here and I keep this sphere of Earth here, and I look through. And whatever areas I find here, let this be a translucent paper. I look through it, and whatever I can see through it, I draw. I draw on this paper, and that is projection. Perfectly, if you want, then you have to look through. While looking through, you have to move your eye. That makes it a parallel projection. If you keep your eye at only one place and look through, it will become a perspective projection, which I explained to you last time. So how do we do? Is instead of trying to do any distortion, we are just keeping a plain paper itself and projecting directly. Now, these type of projections have a certain name. These are called azimuthal projections, which I'll explain to you in the presentation later. Now, instead of having this paper which is kept away like this, and I can see only one half of the earth, one this side of the earth, can I do some more trick? So for that, what we do is we find out that it's a basic fact that this is a paper. Can I convert it, or can I make a three-dimensional shape out of this without distortion? Meaning, is it possible to make three-dimensional shape out of this paper without distortion? Let's try. So the simplest is what? Simplest is I roll it. I make a roll like this. Now, this is a three-dimensional shape and nothing has been distorted. Now, instead of projecting on that plain paper, what if we project on a cylinder and then open the cylinder? That is the simple idea about what is a cylindrical projection. So how do I do it? I take this paper, I wrap it around the globe like this. Okay. Now this is still a flat paper, meaning it has been rolled into a cylinder, but it is not distorted. So I take this paper, roll it around the cylinder, and then from the earth surface to the paper, I project. Now those projection lines can be different, and they can happen in different ways. So what I can do is then project the lines, then draw the shapes as per the projected lines on the paper, and then open the paper. Now I get a flat map. So this is one possibility. Is there any other possibility? Now, something that you may not come to your mind, or something that you may not commonly think, that this plain paper can be made into a three-dimensional shape also by making a cone. See, I make a cone for bed. So this is a three-dimensional shape. This is a three-dimensional shape also. And I can put this earth globe inside this. Here we have a globe of earth which is placed inside the cone like this. And now what can I do? Now what I do is I do the same thing. I draw lines projecting from the center of the earth towards the paper. Wherever they meet the paper, I draw that feature on the paper, and then I straighten the paper. Now, after I straighten the paper, what will happen? Now, on this, I'll draw something on this paper now. If I do a cylindrical projection, what will I get is I will get, I'll just draw it and show you. I will get a map. Sorry. If I have a cylindrical projection, I'll get a map that will look something like this. The grid will be like this. At the edges, it will be further and further. Right? And if I do a cone, then I will get a map which is somewhat like this. I'm drawing it. I get a map like this. Now, this is called as a conical projection. So basically, fundamentally, there are three types of projections, which is with a flat paper. They are called as azimuthal projections. Then there's a cylindrical projection, and then there is conical projection. So these are the three fundamental projections that are there. So let me go back to sharing the screen and show you the same thing in the presentation. Okay. What we have here is I have taken a I've grabbed a video from a presentation, not a presentation. There is a data visualization software called as D3, not software, data visualization library in JavaScript, which is called as D3, and there are many examples of D3 on internet. I have grabbed this video from one of the examples. It's very powerful library which can do projections and maps also. So this is actually a video, and you can see how different projections are possible. This is just a demonstration. So you can see different projection morphing into each other. I think there was some sound of my own while recording. So see here, we can make the flat map in many different ways. Those names were there about, like in the video they were not part. We are going to learn about them in the next presentation. So see, there are innumerable number of ways. Though I've said cylindrical, azimuthal, and conical projections, depending on how you draw the lines, there are more than one ways to draw the lines. There is a vast group of projections, and new ones can be invented also. Many people invent new projections for specific purposes. What basically the three I said, azimuthal, cylindrical, and conical, are three categories of projections. If I can roll this back again, I can pause somewhere and maybe show you some. See here, this is our, it was slightly behind. This is the simple projection of rectangular which I was seeing. It is getting transformed. Sorry. So these are the projections in a nutshell that have been shown here. Now I go to the next part. Still playing. Okay. So the projections, as I said, they fall in three categories. One is azimuthal, cylindrical, conical, which as I already mentioned. Now I show what I've already shown you using a globe. I show the illustration of this here. There's something more that I'm going to show you here about it. Now, this is what? This is an azimuthal projection where I have the paper or the plane kept tangential to the surface of the earth. Tangential meaning it is just touching the surface of the earth. And what I do is I draw lines like this. I've shown it from the side view. We draw parallel lines like this. They meet the surface or the plane or the paper, and wherever each feature meets, we draw that feature on that paper there. Now, instead of the paper meeting in tangent, we can make the paper intersect. What will help that will do? This is a little doubtful in case of this particular projection, but this demonstrates what comes later. Instead of keeping the paper away from it or tangential, we make that plane intersect the globe. And then we project in two directions, meaning whatever is above the plane, we project it below. Whatever is below the plane, we project it up. Now, with this basic principle, what happens is, now if I go to previous slide, in this case, what happens is, whatever is in the center of the globe, center of the paper, that is the least distorted. As we go away from the center, the distortion keeps on increasing, and especially in simple orthographic projection, as we have seen, at the edges, it really gets compressed and we can't even make out the shape. Now, what is intended by making the plane cross as a, what they call is a secant projection. These are called anything that intersects the globe, they are called as secant projection. Anything that just touches the globe are called as tangent projection. This is the secant projection of secant azimuthal projection, which crosses the globe, and we project them from the globe towards down, or from the globe below the sheet towards up. So we project it like that. Now, this is supposed to reduce the distortion slightly, by keeping whatever is the intersecting point, at that point we'll have the least distortion, so that in both the direction when the distortion is there, the total amount of distortion will be lesser, rather than having no distortion in the center. But yesterday only I read a paper that in azimuthal projection it doesn't matter much, but it matters in the other two projections. So now we are coming to the next, cylindrical projection. This is how a cylindrical projection is. I already showed it to you on actual paper. So we wrap the paper in a circular manner around the sphere, and then we project lines like this. So these are the lines I project from the center of the globe to this. Now in this, what will happen theoretically in this particular projection, from the center towards directly toward the cylinder, the actual North Pole and South Pole will never get projected, because as I go near to them, the cylinder point will have to go to infinity. So this is what happens in the projection, one of the projection that we are going to discuss later. But that projection is still useful for purposes which I'll discuss later. So instead of that, we have, even in cylindrical, we have other ways of projecting rather than straight line passing from the center line. Okay. Now, the subject of projections itself is a vast subject, and I would suggest you read. I'm not going to go into complete depth about all possible ways of projecting and all that, because that will be too complex. So whoever is interested, I suggest them to read literature. Just Google geographical projections or map projections, they will get plenty of material. Now, in this case also, we can have a secant projection. And in this case, it is useful, because instead of in the previous projection, this equator, the areas near the equator are not distorted, and we go away from the equator, they keep distorting more and more. Now, in this second projection, which is secant projection, which crosses the sphere, what we do is we have two areas where it crosses. They are called as the parallels, the basic parallels. There's some other word for it, which I forgot, or reference parallels, I think. Now, these are the two parallels. Parallels meaning latitudes are also called as parallel. Parallels is another term for latitude. Now, these are the two latitudes which I have shown here, one northern hemisphere, one southern hemisphere. At those two places, the distortion will be minimum, and in other directions, in one direction, the distortion will go like grow, and in the other direction, that is nearer to the cylinder, the distortion will converge. So the overall distortion remains lesser in this projection. Now, the same thing can be done with conical. Now, this is the simplest conical projection. We have a cone which touches the surface of the earth, and then we project from the center outwards, and then we open. Now, instead of that, we also have a conical. Now, these are the lines, how, meaning from the center, whatever is here, I draw up to the conical surface, and then draw that feature there. I draw the feature here, I draw the feature here, like that. Now, instead of that tangent cone, I can also have a secant cone, which is crossing the sphere at two parallels. And these two parallels are chosen in such a way that where you want the least distortion. At near to these two parallels, you will have the least distortion, and away from them, there will be distortion. In conical, the distortion is different. So this is about the basic categories of the three types of projections which I told you. Now, what happens? Meaning, what is the effect of the projection? That is important to know. As I said, it is not at all possible to project a spherical map on a flat surface without distortion. But what is the kind of distortion? That we don't know. How in what manner it distorts. So that they have done a study, and after that study, they have found out that there are different ways or different types of distortion that are possible. Now, before that, I'm going to show you another prayer. Before talking about these distortions, I'm going to talk to you about, show you a different thing, which is easier to, okay, I think let me continue with this and then show, that is better. Now, what are these different properties of projections? One is the projection that maintains the area equal, meaning the area of what we have mostly seen is area of Greenland looks much, much bigger than India in one projection, but it is not actually. Because in that projection, especially Mercator projection, the areas get distorted hugely. Now, to keep the area, meaning make it in such a way that the areas are almost similar. Areas of different places are almost similar. We can try to retain shape so that the shape doesn't get distorted too much. Then we can try to retain direction. What is direction? Here, direction and bearing, there are two words which may be confusing or which are similar. Direction is we take 2 points on the earth, and direction is a direction from point A to point B along the surface. It will be a curved line actually, as an arc, but we call this as direction. So something that maintains direction. Now, bearing is similar to direction, but it is not just between 2 points, but it's on the path along the 2 points. Now, this was a very important, this is a very important feature in what is required in navigation. When we, earlier days when the maps were made, they were mainly meant for navigation, crossing over the seas between two countries and across the oceans. That time they had to maintain, to reach a certain place, they had to maintain a certain direction. There was no way, all GPS, all those things were not there. So if they wanted to leave from, say, Europe and wanted to go to a specific place in America, obviously America was discovered later, but after that they wanted to go. So you wanted to go to, you have to travel towards that place. How do we travel towards that place? We keep a particular bearing. Bearing meaning the direction of the ship at a particular moment, not point direction between A and B. Direction of the ship's direction at a particular moment with respect to the north, south, east, west. So in a particular map, if you keep a certain bearing towards that, the bearing remains constant. For with a constant bearing, you can reach from point A to point B. That is called as maintaining bearing. And Mercator map is Mercator projection is mainly famous for that. Then we can have a map which maintains distances, equidistant. I mean the distances between 2 points, two locations are same. Now this is easily demonstrated. I'll go back to my GIS software. 10 minutes are remaining. Within that, I will be able to complete maybe the projections mostly. I'll go to the QGIS software where I have already placed something. Now this is QGIS software, and this was the map which we made last time. I have deleted some layers because I didn't want them for this presentation. Now, this map is obviously distorted, as I say, because this is a rectangular map. The areas near the poles enlarge large because all this area near the edge of the pole is actually a point. It's not so much width. It's actually a point. We converge everywhere. So this map, Antarctica is hugely distorted. Greenland is distorted. So these are these are distortion. But how do we know how much is the distortion at which place? From the map itself. For that, someone invented, I think that someone's name is I think Tissot, because it's called as Tissot's indicatrix. He invented a method to mark on the map some circles in such a way that it will show the distortion. So I've already put those circles here, and I'll put that layer on. Now we see some elliptical circles and ellipses here. What are they? These are shapes. Now at the equator, you can see that they look like perfect circles. Now these are shapes. If you take a globe of Earth, if you take a globe, and on the globe, if you draw perfect circles of equal size, on this globe, if you draw perfect circles of equal size and equal distances, meaning properly spaced, whatever number you want and whatever diameter, that is not important. Even in this software, you can do different number of circles. Now, on this sphere, if you draw perfect circles of the same size, how will they look on a projected map? That is shown by the indicatrix. So What happens here, we can obviously see. At the equator, the circles look as almost as circles. As we go away from the equator, here they have become at the 23 degrees mostly. I think it is 30 degrees. I'm not sure. It is 30 degrees. They look slightly flattened, and at the edges, they'll not only look flattened like ellipses, but they also are distorted, meaning they are flattened more on the other side and this side. Now, what we can make out here, obviously, is see the area of this circle below India. See the area of this circle. Now, this area and this area in the northern hemisphere, both these areas are supposed to be the same area. Equal area, because this circular area and this area will be same. Now, if we draw another indicatrix near the green line, it will be still bigger. But this is shown bigger area than this. So this is how it shows the distortion. The indicatrix clearly indicate the distortion. That's why they are called as indicatrix. Now let me change the projection and see, change to one or two projection and see how they change. Let me give a Mercator projection itself. It will distort it further. See, this is the Mercator projection. Now, in this case, what happens? See, they remain circles. So, magic happens. These are circles here, circles here, circles here also. That is how it maintains, because the shape remains the same. The indicatrix shape is always a circle. That is how it is maintaining the bearing. But the area's enlargement is much bigger, meaning as with respect to this is almost twice or more. So this is one projection. Now let us try some other projection. Let me try. Let me try space index, which means we'll see how it is distorted in orthographic projection. See here the shapes near the center of the map vertically, they look almost the same. So this is good in this region. But here the shapes get reduced substantially. They get flattened on the edges. On the right hand edges, they get flattened. At the bottom also, they get flattened. Here also, they get flattened. So in orthographic projection, near the center of the map, orthographic projection, near the center of the map, we get a reasonably good shape, though this is not a circle, this is slightly distorted. Here it is circle, here it would be at the perfect center, it would be a perfect circle. Now let me try another one, and then I'll go back to the presentation. Let me try Molleville. See here. Here what happens is, the distortion is there, but the areas don't change much in the center. Meaning, in this particular map, if I go along the center of the map towards the north, the area is almost the same. Here also the area is almost the same. The area, I think the area here also will be same. It's not exactly an equal area projection, Molly. So there are precisely equal area projections, then equal distance projections, equiangle projections, all those kind of things are there. And there are innumerable number of projections. There are only 3 minutes left. I don't know how many participants are there. So I'll quickly show you the projections, actually different types of projections. Instead of showing in a presentation, I decided to show it on a Wikipedia page directly instead of copying the projections from Wikipedia page to here and showing. And with that, we'll end today's session. I don't know how many participants are exactly there. If there are no participants, then I may not have the second session at all. Let me go back to Wikipedia. Okay. So this Wikipedia is a list of map projections. Here you can see it is a rolling page. You can look at this Wikipedia page yourself to learn more about projections. So this shows a large list of projections, out of which some I'll show you. Some are special. Now this is, and then it lists the type of projection and everything. The most simple projection that we use, or we call it equirectangular or simple as WGS84 is a equirectangular projection, which is this. Now, this type of projection is actually a cylindrical projection, but not like Mercator. In cylindrical, we draw straight lines. In this case, we draw them as curves. The projection lines are drawn as curves. So this is equirectangular projection. Its properties are given here. This is a weird projection because they've ordered them in some way, I don't know. This is an equidistant projection. I have not used this projection much and I'm not too sure, but here the distances, it seems, maintained the same. Now let me go back to some. Now this is the famous Mercator projection, which many people talk about, and it's been a popular projection in the historically for navigational purposes. Here, the areas at the areas near the North and South Pole keep enlarging, and see the Antarctica much bigger than the entire rest of the world also, which is not the case. Now we go to the next projection. I'll show you some interesting projections only now. Webb Mercator is more recently created. Stereographic Miller Lambert. Okay. Now this is a cylindrical projection itself, but they have made it in such a way that the areas remain the same. The shape will be distorted too much. The shape of Greenland is highly distorted here, but the area of Greenland and the areas of other places are in proportion. Meaning here you can see that the Greenland is not larger than India, but slightly smaller than India. Maybe I'm not too sure actual area, but 70-80% smaller. Now, less than 1 minute is remaining. I'll just quickly show you some projection. Now, this is a sinusoidal projection, which looks a little odd. What is the property of it? Sinusoidal, pseudo-cylindrical, not sinusoidal. What is the property? It's an equal area and equidistant. Both properties are maintained. Now, this Molivide, I had used it earlier. I had a doubt whether it was an equal area projection. So it is an equal area projection. It's clearly saying that this is an equal area projection. So now with this, I end the session. It's almost, this is Molivide. Okay. There are several projections here. This is one interesting projection I can show while this is what is called as an interrupted projection. This is okay. Today, obviously, I expected there will be lesser participants. So I had planned that now I will cover something that can be easily understood from YouTube. But if there are any doubts, always you can ask. Projection is over. Now I'm going to try to cover two topics. One is from how to get the software. Now we are going to come to actual working. So from where to get the software, how to get the software, and I may mention names of some other software. Maybe I'll show them on the internet also. So we'll talk about the software and then sources of data. So two things we are going to talk. I will also show you how you can make. I may not make here, but I'll show you a website where you can make maps online directly without downloading any software. Maybe I'll show you even Google Earth. So then I may not go to sources of data today. That much is sufficient for the remaining part of the session. So obviously I'll start first with QGIS because that is the software that we are using. So to get QGIS, what you do is, sorry, I have not started sharing of the screen. Let me 1 moment. I am starting sharing screen. I go to the internet and I search for QGIS. QGIS.org is the obvious one that comes. So you search for QGIS. This is the QGIS website. Now, the first information that it shows is download itself. Then you can support it. Now, QGIS, the current version, as I've shown here, is 3.34. And it is named as Prizren. So they keep naming the different releases or the different versions with the name of some place. So Prizren is a name of a place. Maybe we can even Google and find out where that Prizren is. Now that it has appeared here, let me try that also. In maps.google.com, let me try Prizren. Prizren, it is showing as Prizren, North Macedonia. I'm not sure whether it is the same Prizren, but I hope so. So this is the map of Prizren that it is showing here. And this presumably some map shown on the site also. So it has gone away. Anyway, so what you should do is go to the QGIS site, say download now. Once you say download now, you will get different versions for download for Windows, for Mac OS. There'll be one for Linux, BSD, and there are some apps for mobile and tablets also. I had not checked these. What apps are there? Apps for there are Google Plays. Okay, QField. There are some this thing for getting field data and all that for mm, QGIS itself. I have never used them, so I saw it now only. So you have QGIS available for all operating systems and platform. You download and install. I'm not showing the installation process because I'll have to go through that again, but it's a very simple installation process. Now, once you do that, then I will exit my QGIS from here. I will say this and show you how it appears on starting. So you go to QGIS site, download QGIS software and install it. After you have installed, you will have the icon on your computer. On my computer, it is this. So I start QGIS. Now QGIS Prizren is starting. Sorry. QGIS has started here. And what it is showing me is the projects that I had created last, because it shows a lot of projects. If when you install it for the first time, it will not show any of this. So what you do is this is what you will get. Now in this, the layers panel will almost always be there. So what you can do now is start the project or start new this thing. I'm not going to show you detailed working of this software right now because not many participants are there. I would prefer somebody is there, and then I'll show different workflows. But basic, I'll show you the overall working of this, meaning just the gist of it. So what you have is on the start screen, you get on the start screen, you will get this. Where is my bar is coming in between? Okay. I started recording. I was not too sure. Just let me stop it and check once. No, the recording is started. Sometimes I have this doubt and I can't make out from the screen whether the recording is on or not. Okay, so these are the different panels you'll get. Let me start with a new project. So this is what you'll get when you start with a blank project. It will say untitled project. Now there'll be toolbars here. Now these toolbars will vary depending on what you have chosen or not chosen. So you can customize them. You can customize the way you want. On this side, you will have this panel, which is the layers panel, and you'll also have the browser panel by default, mostly, which can again change. You can even disable this and you can do many kinds of things. So then how do we see the different panels? You see in view, there are panels which you can put on and off. So this is how we control how we see the interface. In the panels, we have different panels which you can put on and off. And then we have toolbars which you can put on and off. So what is a panel? Panels are these panels. This is the first and the most important panel is the viewing panel. Then this panel is the layer panel. So here, if I see how many panels I have layers panel on, browser panel on. I can put them off also. Then I have processing toolbox, view, this, that, many panels. Toolbars are these, what you see on top. Now I can maybe move a toolbar. See here, I have moved this toolbar. This is the Indicatrix toolbar. And again, place them somewhere else. So when you move it, then you can know which is a distinct toolbar. Otherwise, it's a little difficult. Now, see, this is one toolbar which I have moved. Now it will show the different. Now, if you bring it near here, it will show you what that toolbar is. This is a digitization toolbar for digitizing a map. Now, if I bring it to near to this, here it is not showing. It is not showing that it is an Indicatrix toolbar because maybe it is a customized toolbar. So we have various toolbars here which you can put on and off depending on your need. Now this is an advanced digitization toolbar. I put it in place. So you can put those toolbars on and off. Now, other menus like view menu, project menu, settings menu, all these things, some of them I'll cover in later sessions when I'm talking only about this QGIS software. I want to show you one thing interesting here before that. There is what is called as a plugins menu. And this software comes in with a huge number of plugins. Now you see here. Now you can install the plugins as you want. Now we can, one of the plugins that I've installed here is the Quick Map services. See here, you have a lot of plugins. The Indicatrix, which I showed as demonstration for sites, is also a plugin. If I disable this plugin, it will go away from the toolbar. The plugins, when you enable them or disable them, they'll have a toolbar, or in addition, they'll have a menu option or whatever. So this plugins is a very interesting, very interesting feature with which you can get a lot of different features which are like add-ons. It's like add-ons. So there are a huge number of add-ons, and in addition, there are other add-ons which you can probably download, but most of them are accessible from here. You can search them on the internet, whatever you want. Mostly you'll know about a plugin when you do some Google search and know about some techniques. Then it will tell you that this plugin you have to use for this purpose, and then you try to get that plugin and install it. This is in addition to the built-in features, built-in default features of QGIS. So this is the QGIS software which we can download, and obviously that is the main software that I'm using. Now, instead of QGIS, suppose if you want, or you don't want to download any software, then what you can do is you can create your own maps also using what, and let me show you other application which I want to show, which is ArcGIS. Which is Google Earth. Google Earth is a software which you can use online as well as on your computer. Now, if you buy these days, if you search for Google Earth, you will not easily get the version that is downloadable. So you'll have to do a lot of work and find out somewhere to download a downloadable and installable version. So because they have switched over to online only. So this is Google Earth. Google Earth is mostly you think it as a way of browsing the Earth, but it's not. You can actually create maps and do lots of things. So let me directly go to my town. I'll say Yelahanka. Yelahanka, Newtown, Bangalore, Yelahanka, Bangalore. Okay, so it is used for browsing, as I said, as well as for creating and drawing maps. So I have come to Yelahanka. This is earlier also I have come to my place. Now what I can do here is directly I can start creating maps. I say edit. This title, I'll say test. Now add. So I can keep creating a map here. I'll just say I add a place mark. So wherever I want to say I'll mark my house, might mark my building here. You can name it my building. This is a very easy way. If you don't want to download any software and still create some maps, you can do it using Google Earth also. ArcGIS Online as well as Google Earth. So I have marked one point. What I had shown that day is drawing this um, lake. Instead of that, though I have marked my place here, I will draw another lake today or show you how to draw. I will not completely draw it. I go to add path or polygon. I add, say, I choose and click path or polygon and I keep adding. So now path and polygon, they might combine. Online software, one advantage is that you get the latest features, but the other disadvantage is that they keep changing the interface. Now, this interface also I was not used to seeing this big circle here like this and all. I'm not used to in Google Earth because you mostly use the installed version of Google Earth. Now, what I see is if you come now near to the starting point, it will close the point. Closed shape it is showing here. So I have closed the shape. Now it has created this shape. Now you can save this as a save to project. Untitled polygon, I'll just say lake or whatever. I have not named anything. I'll say LM College. And I'll save it. So I have in my project, I have two features which I have already added. Now what you can do is you can export them. Tile overlay and it is same slide. No, that is a folder. Here you can switch. Export is where now. Tools. No. Just saying. It will save my project online, but it can be exported as what is called as a KML. Try to edit feature. Again, there's some change in interface. So I'm not getting to now. Okay, I think it will be in the file. This file, yes, export. Export as KML file. So this project, whatever I have done is it is saving. It will now save it on my computer as a uh, this thing test file. Now I can open it here. So I have got this test.kml. I'll show you how to open this also. Now it is saved in my downloads. Now what I'm going to do is I'm going to show you an installed version of Google Earth, which I have installed, which is a little tricky to get. Nowadays, they have kind of made it deprecated. So the other software which I'm showing now is the Google Earth installed version, or what did they call as Google Earth Pro. The interface, the data will almost be the same, but the interface is completely different. This is much more, I'm used to using this because this is what I use often. Now what I'll do is I've saved a file from the previous online version of Google Earth. I'll open that file. And I'll open it from my downloaded documents. The file that is normally will be saved will be KML. The moment I open the file, it will go to that location. So see here. This is my building I have marked, and this is the polygon that we drew in online version of the Google Earth, and which I have done. Now this can also be opened directly in QGIS. Let me go to QGIS. So I'll say, I'll drag and drop better. I'll go to my downloads. Sorry, I'll go to my downloads folder and take this test KML file. And drop it in this. See, there are two layers. One is a point layer and a polygon layer. So it is asking me to add. So I have added both the layers. So here I can see now there's no base map here. There's no base reference map. So I can't make out where it is. But this is the point that it is showing and the polygon. So I have directly, what I've done now is I've used 2 or 3 different software. I have used 2 versions of Google Earth. I've created a map in online version of Google Earth, opened it in installed version of Google Earth, and opened it also in QGIS. So here, now I'll try to show you the advantages of this or how you can use this. The basic advantage of having Google Earth Pro installed is you have all the data saved on your computer itself. I'm an older person, so I'm used to more of this concept. Nowadays, people are not afraid at all of saving their data only online. I'm still now, though I have shifted to backing up all my data online recently in last 2-3 years. All my backup of I still maintain a backup of all my 30 years of work almost. It is all online now. But I still am a little skeptical about keeping the data only online. I want it in my computer close to me. So I prefer these software which work on your own computer and save the data on your own computer. Yesterday I was talking to a neighbor. He was asking me what was the training that you're conducting. I said I'm using GIS software and all that. But all that is not necessary. That there are APIs. Yes, there are APIs, but they will take the data from online, only show you online, save it also online, which I'm not comfortable with. And obviously, there are other advantages of having the data on your own computer, the different types of analysis you can do, you can share it between different software, and all that is different matter. But these days, currently, there are people who work with data only online, especially in employment scenario. Most of the data is only online. It's not on your computer. It's not even allowed. I'm showing you both. You can have the data online as well as on in your computer. And in Google Earth, all my data, whatever I have done for most of recent time is here. It is all gets saved in my places, and I can uh, show you, see it the way you want. And I have different types of data here. Recently, I had last year, okay, I should say last year is correct. I visited Europe. So I was fascinated by the Rhine, and I tried to Rhine River, and I tried to also by the bridges. So I tried to make place marks of all the bridges on the Rhine. It's some project that I'm fascinated in doing, but uh, I have not continued on it. But it's interesting to do some things like this. So here, these are the bridges on the Rhine River. You can see many of them, which I have marked as points. So all this data remains saved in your computer, and you can use them the way you want. Now, by the way, this is uh, another one. Now, this is an industrial area in Delhi where I had done. I have marked it industrial in area in Delhi where I had done a lot of work, CAD work and water supply and all that kind of work. So it is seen here. So I have kept it marked. So you can keep all your kind of place marks, bookmarks saved in your own computer. And for safety, you can also export them. You'll also export it and save it as whatever, and it remains safe. Now, what else you can do here in Google Earth is there are different layers. So there's already a database which you can see borders, places, photos, roads, 3D buildings. You can put all of them on. Let me come back to India. Let's see India. So it will show me India border now. I put the borders on, I guess, see here. So now it is showing me all state borders and other borders. You have all these different layers which you can put on and off. Borders and labels I have removed. So this is gone now. I can put it on. Places is on. So I can see different places. And as I zoom in, it will show me more and more places. I have the roads here. Roads, I'll put it off. So Google Earth Pro is a good software. You can use it practically like a GIS software, and you can do lots of things. There are things which can do. I can show you here. Let me show you some terrain. Let's go to Himalayas. Okay, let me go to Everest, which I have marked. If you want to see the terrain, say what I do is I draw a path. No, I choose a place. Sorry, I add a path. Okay, now okay to this path. Now what I can do is show elevation profile. I have what I have done is I have just made a path across the Everest, and here I can see the elevation profile. I can move along this. See here. Along that path, the arrow will move. You can see the arrow moving in the upper window, and it shows where it is, how much tall it is. These are the two highest points, 7988 meters and 8086 meters. And I move along, and then we come down to the plains. So these are the different kinds of software which you can use either online or offline. QGIS is there. RGS online, I've already told you. There are other two software which are not working on this computer, so I can't show it to you, but I could show their website. One is obviously the most used GIS software is ArcGIS. ArcGIS Online was the online version. ArcGIS is the software here. ArcMap is the software that is used in ArcGIS, and this is a Wikipedia page. I can show you a screenshot of this here. So this is how the ArcGIS software kind of ArcGIS installed software. Okay, this is how the ArcGIS installed software looks, similar to QGIS, but it is the most popular and it has got a lot of features. QGIS also got, but this is a more powerful commercial software. Similar way, there is a software called as there's a software called as Global Mapper, which I use commonly. Global Mapper is a software that is, both these software are available only on Windows, so I don't have them on my MacBook Pro. Global Mapper is also a popular software, which is not as powerful or as well known as ArcGIS software or even QGIS. But Global Mapper, in my opinion, or my use, I use it a lot. Global Mapper is the best software if you want to convert from one format to another. It's much quicker. You don't have to do a lot. You just insert data from one one type of source and just export it. Just directly import it, export it. So I find Global Mapper is the best software for converting between data type without any. There might be some small errors because ArcGIS Online, ArcGIS and all, even if there's a slight mismatch between data terms, there's that it starts giving you errors, giving you warnings. It doesn't do any half-cooked job. But for most of the purposes, you don't need that much accuracy and that not precision. That time it's very easy to use Global Mapper and import and export data. You can use that software also. especially for importing, exporting data, changing between different formats. Uh, I cannot show them here because I have them on another computer. So these are the basic software, and there are many other software. If you search, there are many other software for GIS that I use. One of them is earlier there were two software. I mean, long ago, before all this came, there was only two software: ArcInfo and MapInfo. MapInfo is also there now, called as in some other. There are some other versions of software on Windows, newer software, but you don't need many of them. These whatever software I have shown so far are sufficient enough for doing any work. In fact, RJS is people work only with RJS, only with QJS. I prefer, as I said, Global Method for conversion. I prefer Google Earth for saving my own data from this by browsing on Google Earth and then using it elsewhere, exporting to KML and all that. And so that is about the brief about the different software. Next Sunday, I'm going to talk to you about the different sources of data. So, which will be the most important session. And with that, on next Sunday, I'll end this season of this training what I'm doing, because I cannot take these sessions in the next month. In February first week I'll take, but in the second week I cannot take. I'll be going outstation. So after that, I would probably do different workflows for doing specific kind of work in QGIS, or using specific kind of maps, which will be basically workflows. Next session, I'll try to do sources of maps and symbology. That will probably complete whatever is minimum necessary to create your own maps. So whoever wants to attend, please, I request all to attend. The next session will be the end of this, what they call a season in serials. I call it also a season. And then I'll come back again after a month or so, depending on what is the plan I have. So I'll stop here and stop sharing also. You can ask for any doubt now? Or I'll end the session. Tell me.
Yes, sir. Good morning. I I wanted to know about okay, so these are many different options of having a QGIS software. So
Yes.
any particular one which is more proficient in 3D data or something like that? Like, you know.
No, basically, as I told you, 3D data QGIS also can handle, as well as RGS can handle. 3D data, if you want to handle, it depends on what you want to do. Basically, as I told you, the basic layer of GIS software is thin. Meaning the basic fundamental layer of all GIS software is thin. And then there are verticals about different applications. Now, it depends on what is your workflow, what is the purpose. Meaning, if you want to say 3D data, the basic question would be, what do you want to do with the 3D data? Do you want to create a 3D printed model? Or do you want to create a 3D data which is for engineering applications? Or do you want to use 3D data for something else? It depends a lot on that. Now, these are all basic GIS software. Now, what happens is, since my primary expertise is AutoCAD, I started with AutoCAD 30 years ago, and I've been using AutoCAD. And even in GIS, I started first with AutoCAD Map, though it's not known as a GIS software. AutoCAD Map 3D, it's named as AutoCAD Map 3D. It is basically more for engineering applications. So if you have 3D for engineering application, then instead of a direct GIS software, you might have to consider AutoCAD Map, or better still is AutoCAD Civil 3D. So it depends all on application. AutoCAD Civil 3D is something that does very good work with 3D terrain and 3D map.
Mm.
So it is meant for basically for engineering. As I said, Civil 3D is meant for civil engineering work. So that is one of the best for Civil 3D. Now, what happens is, meaning I talked about one end, if you want to do some construction work, civil engineering work. The other end is now, which is very recent, has become data acquisition, what is called as the LiDAR data. You have
Mm.
what is called? I did forget the word.
Drones.
You have drones with LiDAR mapping device fitted on it, and you can actually do the 3D mapping of a terrain using the LiDAR data. Now, the LiDAR data is acquired in the format what is called as a point cloud. It is just a cloud of points. Now, there are various software again which can handle point cloud in a more efficient way in different ways. Again, Civil 3D is one of them. And then there are highly specialized software which are for point cloud mapping, and then they convert point to features. Like, for example, if I do a point cloud mapping or a LiDAR mapping of a city, it will just come as points. It will not come as features. You will not be able to, you will be visually able to make out that there's a overbridge here and a flyover here or a river there or whatever. But to the software, it doesn't make sense. It's just a points. Now, there are specialized software to convert the 3D LiDAR data to features by trying to detect them. So it all depends on what is your application, and I'm actually not an practical expert in using all this software for all kinds of applications. I've used terrain data for civil engineering, which is mainly for water supply and all that, where I had used Civil 3D, meaning get terrain data. As I showed you, you can get the terrain data from internet also or from survey. Use it for civil engineering application. So it all depends on application. The session will end now.